We're going to continue our discussion of capacitors today, and the first thing we're going to do is talk about a dielectric, and we're going to look at what that is, and how it changes a capacitor, how it changes the electric field of a capacitor, and how it changes the voltage of a capacitor. A dielectric essentially is something, a non-conductor that we're going to put in a capacitor. Then we're going to put capacitors in series and in parallel, something that should be familiar to us from last year when we discussed circuits in general, and look at how the charge on those and the voltage across the capacitors is affected when we put them in that way. And then we're going to look at sort of a complicated dielectric situation. So, getting into dielectrics. Dielectric is a non-conductor, essentially. Anything can be a dielectric. Water sometimes is a dielectric. It's not the best one. So let's say we have over here a normal parallel plate capacitor. Plus Q on the top, minus Q on the bottom, and separated by a distance of D, just like before. And the capacitance of this thing that we found before was the area of the capacitor. I didn't draw that in there, but you know it has area, times epsilon naught over D. And we spent a lot of time getting to this. Now, what we didn't do was talk about epsilon naught. See, that epsilon naught describes what's inside of the capacitor, and right now we have nothing. So that epsilon naught tells me about nothing. It's the permittivity of free space. It tells me how an electric field behaves in free space. When we insert a dielectric into something, let me erase that real quick. When we insert a dielectric into our capacitor, let's say we have the same capacitor, same area on top, same separation D, same positive Q and negative Q, but we're going to stick inside of this thing a dielectric. Let's say it's a piece of plastic. We're going to put a piece of plastic in here. In a real life situation, that piece of plastic would fill the entire space. Now, inside of this piece of plastic, and I'm only going to draw 3 of them, what happens when we put it in that electric field is that the molecules, and yes, there are more than 3 molecules, get polarized, and they shift a little bit. Now, they're not going to move around, but we're going to have a negative towards the top and a positive into my molecule towards the bottom. And that's going to affect how the electric field looks inside of my capacitor. Now, the electric field kind of gets broken up. It points straight towards these negatives. That's normal. And from the positive here to the negative here. But what we see is a tiny, inside of the molecule, if you will, electric field pointing upwards. What we've done is decreased the total electric field in that area. Because over here, in the normal capacitor, that thing just points straight down. The electric field is constant all the way through, and it's its strongest when we're right here. So, the dielectric broke that up. Now, the way we quantify that is instead of saying that it has a permittivity of free space epsilon naught, it's just epsilon. Let me change this. And epsilon is equal to our dielectric constant kappa. Looks a lot like an A, but we're going to call it kappa, times epsilon naught. And this kappa thing is bigger than 1. So what we see is an increase in the permittivity of the space in between these things. So let's look at how that changes the electric field. We all know how the electric field outside works, so we're not going to look at that. But if we draw our little Gaussian surface right here, and we do Gauss's law, E dot dA is equal to our Q enclosed over, instead of epsilon naught, this time we're going to have epsilon, or kappa, times epsilon naught. So we know it's E is equal to, after we do everything, Q over A times kappa times epsilon naught. we have decreased our electric field. It is smaller than it is over here. So between these two, I know the electric field is smaller. When we do the voltage, that is the integral of the electric field with respect to radius. Since it's constant in that area, really, it's just the electric field, Q, over A times this new kappa times epsilon naught times the distance separating those two plates. And I see here again that because of this kappa, I have decreased the voltage. And when we solve for the capacitance of this new thing, it's kappa times A epsilon naught over D. Because of this new dielectric, because of this new sort of new way that the electric field works in that space, we've increased the capacitance. This is why we use dielectrics before. If you go and buy a capacitor at Radio Shack and cut it in half, you'll see metal and then sort of this black plastic stuff. That black plastic stuff is the dielectric. What it's doing is changing how the electric field works so that we can increase the capacitance here. That's really all there is to a dielectric. You put any dielectric in any capacitor, fill it all the way up, and you're going to increase the capacitance by a factor of the dielectric constant. It's a very straightforward thing. It's going to get more complicated after we look at capacitors in series and parallel, but for now, it really just increases the capacitance because it decreases the electric field and it decreases the voltage. It allows me to store more charge against a certain voltage. It allows me to store more charge against a certain voltage. So if we were to imagine sort of a situation where this would happen, say we take a battery. Let's say we take a battery, and to that battery we attach a capacitor. Now, that's the symbol for a capacitor. That battery is a source of charge, and what it's going to do is pump positive charge from the positive end of that thing to the top of the capacitor. It's going to fill it up really quick. But let's say my battery has some certain voltage. It's going to charge my capacitor to a certain voltage. Because they're connected, they're going to have the same voltage. Now if we come in here and we add a dielectric in here, it's going to charge it to the same voltage. But let's compare what happens with the amount of charge that we have in there. Beforehand, my charge Q, well, if we remember for a capacitor, capacitance is equal to Q over V. My charge originally would be the capacitance times the voltage. Once we add this dielectric, though, my new charge with the dielectric, we'll put a little d right there, is going to be not CV, but kappa times my old capacitance times the voltage. I've increased it, again, the amount of charge that I can store on this capacitor by a factor of k. That's also going to increase the amount of energy I can store. That's something to think about when you're building capacitors for things. So, that's the basics of how a capacitor works in a circuit. We're going to look at what happens when we connect multiple. So, let's look at capacitors in series. So, to start with, we're going to have a battery, and we're going to connect one capacitor here, and one capacitor here. We're just going to do two, and they don't even have to have the same capacitance. So we have the battery with a voltage of V, capacitor 1 with its capacitance, C1, capacitor 2, its capacitance, C2. Now, again, we have empty space between these capacitors, so if we're thinking of this like we thought of circuits last year, this wouldn't necessarily be a complete circuit. I don't have a smooth path of conductor. So, because of the battery, I'm going to get a certain amount of charge, positive Q, to build up on this side of the capacitor. Because everything here is a conductor, though, it's going to induce an equal amount of negative Q on this side. But because this thing now has negative Q and those negative charges had to come from somewhere, I have the same positive Q over here and the same negative Q back here. What I see in series is that for each capacitor in series, the charge is the same on each capacitor. So the total charge that we're talking about in this system is equal to the charge on capacitor 1, we'll call it Q1, is equal to the charge, oh no, it's not an equal sign though, is equal to the charge on capacitor 2. They're equal. Now if we're going to look at this in terms of voltage, that voltage is going to be split between these two things. As we move around the circuit, right, we have to have zero voltage. That's something we learned about last year. So if we start here, we pick up some voltage, we're going to lose some across the first capacitor, lose some across the second capacitor. But the total voltage of the battery has to be the same. So we see an additive thing. The voltage of the total voltage is the voltage across capacitor 1 plus the voltage across capacitor 2. This is another rule for things in series. We see that the voltage adds. And the reason I'm stressing these 2 points especially is because when we look at circuits with resistors, those two things stay the same. So the charges are equal, the voltages add. Let's see what that means for capacitance. And again, capacitance is Q over V. So if I solve that for V, it's Q over C. I'm going to take that and substitute it in right here. So I'm going to have Q total over my total capacitance is equal to Q1 over capacitance 1 plus Q2 over capacitance 2. Now look at what's going on here. Because I know that Q1 and Q2 are equivalent and equal to the total charge, those all cross out. And so when I put capacitors in series, I see that we have sort of a weird way of adding them together. The total capacitance of the system actually decreases. And we see that 1 over the total capacitance is equal to 1 over C1 plus 1 over C2. And if I had 3 and 4 capacitors, it would be 1 over C3, 1 over C4, on and on and on and on. Forever, however many capacitors I have. This is how capacitors work in series. Charges are the same because of that induction thing. The voltages add, and the capacitance adds in this weird way. That means that the total capacitance of capacitors in series is less than the smallest capacitor we have there. It's a good thing to note. If we go on and look at capacitors in parallel, we see something a little bit different. Now we're going to have to redraw our circuit, have our battery, voltage of the battery. We're going to have one branch. On that first branch, we're going to have a capacitor. Call it C1. Comes back. And on the second branch, we're going to have a different capacitor. Call it C2. And it's going to come back. Now, because of the way charges work, the battery is going to pump out charges and fill it up. And I'm going to have a charge, positive Q1, sitting here. Of course, that's going to induce negative charge on this side, but that comes from the negative end of the battery. And we're going to push charge out to here, and I'm going to get plus Q2 sitting on this capacitor. Now, in this situation, they don't have to be the same because they're not inducing charge from each other. So Q1 and Q2 aren't the same here. In fact, in parallel, we're going to see that our charges, total charge, add. Well, the total charge on this thing, these two are different and in no way related to each other. So Q1 plus Q2 is my total charge. Q total is going to be Q1 plus Q2. At the same time, I know that anything attached to this battery is going to have the same voltage as the battery, and it's going to have 0 voltage over here. In parallel, the voltages are equal on the branch. For each parallel branch we have, EQ, I didn't do that right, equal. So I see that the voltage total is equal to voltage 1 plus, nope, is equal to voltage 1 is equal to voltage 1 is equal to voltage 2. They're the same all the way through. And again, remembering capacitance. Capacitance is Q over V. We're going to plug that in here to find out what's happening. Well, capacitance is Q over V, and Q is equal to C times the voltage. We're going to stick that in right here. And we're going to see that capacitance total times the total voltage is equal to capacitance 1 times voltage 1 plus capacitance 2 times voltage 2. And since the voltages are the same, they're going to cross out. And we see that the total capacitance here is just the two things added together, C plus C2. That's the total capacitance here. So when I add capacitors in parallel, I increase the total capacitance of the system. I increase the total amount of charge that I can store. That's the basics of that. Now, split capacitors offer us an interesting problem to look at. Let's say I have my top plate. I'm going to draw it right this time. I'm going to put our area on there. It's got area A, and on this side we're going to have charge Q. Same thing with the bottom plate, area A, charge negative Q. It's ugly, I get that. Separated by a distance of D. And in our first situation, we're going to take a dielectric, and we're only, oh, I wanted red. We're going to take a dielectric, and we're only going to put it on half. So this is a dielectric of kappa, and in the, if we want 3 dimensions, we're going to put it in half, okay? And the other half, we're going to have nothing. So essentially, I'm going to have 2 capacitors. One that's got something in the middle with a dielectric of kappa, area A over 2 on top and bottom, and separation of D. And the one right next to it is an empty one. Here, we'll put our plates in here. Same separation of D, same area over 2, but inside of here, kappa is equal to 1. I got free space. I got no dielectric, so it's going to act just like it did before. So this capacitor, C1, is going to be kappa times A epsilon naught over 2D. And the reason it's over 2D is because I have half of my area. And over here, C2 is just going to be A epsilon naught over 2D. And if I want the total capacitance for this thing, this split capacitor, it's just going to be C1 plus C2. It's like I have 2 capacitors in parallel. They're right next to each other. The total charge on this thing is going to add together, just like 2 parallel capacitors. So the total capacitance here is going to be A epsilon naught times kappa plus 1 all over 2D. That's what happens when the capacitor is split in this way. Another thing we can look at, and I'm not going to draw the area this time. We have our area on the top, area on the bottom, but we're going to take and only fill it halfway with a dielectric. A dielectric is going to have constant kappa, and then nothing down here. If we want to think about this like a capacitor, it's two capacitors in series. The first one being kappa times A epsilon naught over half of that distance, which is D over 2. And this next one is going to be A epsilon naught over D, and it's half D, so that 2 goes to the top. But they're in series. Since of this system, I gotta add it up weirdly. 1 over the total capacitance is equal to the inverse of capacitance 1, D over 2 kappa times A epsilon naught. 1 over capacitance 1 plus 1 over capacitance 2, D over 2 just times A epsilon naught. No dielectric constant there. So, adding these together, a little bit of tricky math, I got to multiply this by kappa and this by kappa. Now I can add them together, and I see that 1 over C total is equal to D times kappa plus 1 over 2 kappa times A epsilon naught, and that my total capacitance in this situation is equal to 2 kappa times A epsilon naught over D times kappa plus 1. It's a different way of adding them together.